Alright, here is a focus lesson on thermal expansion and contraction. So let's think about a solid that's made up of a bunch of particles packed pretty closely together. I'm just going to draw a 4x4 grid here. And so you already know that anything that has a temperature, hopefully, anything that has a temperature, then that means these particles are in a little bit of motion at least, even if it's really cold. So all these particles are kind of shaking back and forth a little bit. You know, they're kind of, since it's a solid, the particles aren't sliding around like in a liquid. They're locked in place, but there's still a little bit of vibration. There's some shaking going on. Maybe those last two arrows are a little on the big side, but so every particle in here is kind of wiggling around a little bit. But if we add heat to those particles, what we get then is more motion, and the particles shake around more. And so with that extra motion, you know, if you're going to do extra motion, you need extra space. So now these particles are wiggling around back and forth in larger zones, you know, moving up and down and front and back, side to side, all that stuff. So if we take a look at this, we say, all right, so this would hold that bunch of atoms, and if we heat up that same bunch of atoms, now if you wanted to put them in a box, you would need a box this big. So as temperature goes up, if temperature goes up, then the length goes up. Or I guess, you know, like the length would be if we're looking at, say, this side versus this side, you know, little L versus big L. You could also say that, like, if we're looking at this area, you know, the area of any one surface goes up. You know, this area right here is bigger than this area. You could also look at it, let's say that we were thinking about a 3D cube here. And this 3D cube would be this big. I'm making my drawing really ugly here, but that's okay. And this 3D cube would be this big. So if temperature goes up, then the volume goes up. So this is what I wanted to cover in this video: thermal expansion and contraction. So if you take the temperature up, these things go up. If you take the temperature down, then those three things go down. What does this explain? This explains things like in bridges. You drive over bridges and you hear, as your tires go over, you hear dum 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 dum. And the reason why is because you're driving over these expansion joints. Sometimes they're like metal fingers that kind of interlock with each other. Sometimes in bridges there's like actually like rubber bumpers. Let's see if we see one of those. And sometimes it's just, you know, an open gap. Like right here, this is like in somebody's sidewalk or a driveway. You got to put in these expansion joints, or otherwise your cement will crumble because it's brittle. Apparently, when I googled expansion joints, apparently expansion joints in pipes and tubing is a big deal. It looks like there's all kinds of pictures of these expansion joints for pipes. So like you hook one end of a pipe on here and the other end on here, and this thing is made to flex as the temperature changes. And here's a rubbery looking one, and right here is like a rubber bumper like in a bridge or something. So anyway, of course, there is an equation that we use to describe this, and it is the change the change in length equals a constant. That's an alpha. I guess you don't really need to know that, but the change is a constant times the original length times the change in temperature. Pretty straightforward equation. It's actually not too big of a deal. So you've got your constant, you've got your length original, and you've got your temperature change. One thing to be careful of here, when you look online or in books or wherever, these temperature changes, if you're looking for a given substance with a given coefficient, these are going to be in probably degrees Celsius, which is the same thing as degrees Kelvin, or just kelvins, I guess. So if I want to solve one of these problems for you, I'm going to have to pick some substance, and I'm going to have to go out and I'm going to have to find its coefficient, or its constant, its what do we call these things? Thermal expansion coefficients is the official name for them. So let me do that. Let me go here and let me do this. Coefficients of linear expansion. So let's say we're talking about aluminum, and it's 22.2 times 10 to the negative 6 meters per Kelvin. Okay, so 22.2 times 10 to the negative 6, and so we're in meters. And aluminum is 22.2 times 10 to the negative 6th. So this right here, this number, is what goes right there. That is our coefficient. So now let's just make up a problem. Let's say that we've got an aluminum wire running from your house to your barn or something. And let's say that it's 200 meters. Okay, so 200 meters from your house to your barn. So let's say our original length is 200 meters, and the original temperature is, let's say, 10 degrees Celsius. And let's say it's going to heat up from an original temperature of 10 degrees Celsius. Let's say it's going to heat up to 30 degrees Celsius. So pretty good change right there. So what I'm going to try and figure out then is, how much does that length change? Oh shoot, I didn't pause it. I just wasted a bunch of seconds. Oops. Okay, so I'm going to insert a new page here, and the equation that we had before was the change in length equals the constant times the length original times the change in temperature. But what if we're talking about, instead of length, what if we're talking about an area, like the size of a floor or a wall? Well, areas have two dimensions, length times width. So we could just take this coefficient and do this. And then it's essentially, you know, the same equation, just with that 2 in there. Or what if we're talking about volumes, like a tank full of gasoline that's super duper full and it gets hot? Will the gasoline expand? Yes, it will. So volumes have 3 dimensions, so we could use this. These 3 equations, so this one solves for changes in length, this one solves for changes in area, and this one solves for changes in volume. So I think now would be a good time for me to, I've already solved one length problem for you, so let's solve a volume problem for you. So let me do this. Let me draw myself some kind of a big tank, I guess. Like a big rectangular tank. Okay, I've done better, but that's not horrible. And it's filled with, partially filled with some kind of a liquid. And let's go figure out what liquid we want to use here. What on this list is a liquid? Okay, so gasoline. Say it's gasoline. And its expansion coefficient is 317. And that's times 10 to the negative 6th. Okay, so let's pick, let's say that right now in this tank, let's see how big this tank is. Let's say this is a pretty good sized tank. Let's say it's 2 meters by 2 meters, and let's say that there's 1.5 meters tall of gasoline in this tank. Maybe I shouldn't use blue, but oh well. So, what would I want to know? You might be thinking I'm making you a volume problem here, but I don't think that's what I'm doing. I think if I had this tank, and let's say that this tank was imaginary. Let's say that it doesn't expand or contract at all. It's just this tank stays the same size. It has no expansion coefficient. So what I want to know is, on a cold day when it's 0 degrees, this is what the situation is. And then let's say I come back in the summer and it's a blazing hot day. Let's say it's 30-something degrees Celsius. I want to know how much higher the volume in this tank is going to be? Do you think it would be something that would actually make a difference, something we could measure? So let's do it. Let's do this one in green. So the change in length, because we're just measuring this length, how much taller the gasoline is going to get, the change in length is the coefficient, which was 317 times 10 to the negative 6th, times the length original, and we said that that was 1.5 meters, and then the temperature change was 30 degrees. Okay, so doing this, we're going to go, okay, so 317 times 10 to the negative 6th times 1.5 times 30, and we get 0.014 meters. So, or that's 1.4 centimeters. Okay, so the difference between, you know, winter and summer or a hot day, the gasoline in this tank is going to go up 1.4 centimeters. And that might not sound like a big deal, but what if this tank was already full? I mean, then your gasoline would come spilling out, right? So then it is a big deal. And those are the kinds of problems that engineers have to solve when they're designing gas tanks in cars and so forth. You know, are you going to make your gas tank a little bit flexible, or are you going to have some kind of an expansion joint things going on somewhere? So what if we wanted to do this same problem, and instead we wanted to know how much the volume overall changed? So what would that be? It would be the same equation that we used last time. It's just that we've got this 3 in here. So I'm not going to write it down. I'm just going to hit the numbers in the calculator and see what happens. So I'm going to go 3 times, and it was 317 times 10 to the negative 6th times 1.5 times, and then the temperature change was 30. So I get 0.042. So delta V, I got 0.042. Is this 3 times bigger than this? I guess I should have drawn my arrow at that, but so let's just do that. So what if we divide that by 3? Yeah. So there you go. The volume change is 3 times as much as the length change, and that's because volumes have 3 dimensions: length, width, and height. So I think I'm kind of done with this video, but something just popped into my head. So does this mean then that in the summertime buildings are taller? So like if you had the Empire State Building or some other Big Daddy tall building, would it actually be taller in the summer? Yeah, that's true, it would be. And the bigger the thing that you're talking about, the bigger of a deal it is. So like think about power lines. You know, you see power lines that go, you know, from Beaverton to whatever town far, far away, and the wires that they wrap, or the wires that go from pole to pole, they sag. Have you ever noticed on a hot summer day that they seem to hang lower than in the winter? Well, it's because they do, because the wires are a little bit longer in the summer. So you know, that's something that the electric companies, when they build this stuff, they plan for that kind of thing. So that is how you solve a thermal expansion or contraction problem.